Hello, so welcome to this video. So in the last video in the playlist we looked at invariant quantities, which all observers agree on. And this is important in special relativity because we want our kind of equations of motion to be ideally equations that all observers will agree upon no matter their velocity, because otherwise writing laws of physics becomes incredibly complicated. In that we would need to kind of hold different sets of equations for each possible velocity, and as there's an infinite number of possible velocities, that is a lot of sets of equations. We mentioned also in the last video that whilst this invariant quantity, which all observers agree on, is related to the length of a vector in space-time, and we call this vector a 4-vector, different observers will disagree about the components of this 4-vector if those different observers have kind of relative velocity to each other. And it's this kind of disagreement, for example, in the case where we're considering the 4-vector to be 4-position, that can lead to kind of like, that's like time dilation or length contraction, because 4-position has components of time interval and space interval, so when you jump reference frames, that is, when you move to a coordinate system or new coordinate system, but where you yourself, along with the coordinate system, are moving relative to the stationary observer, then you will look at 4-position differently. You will see it having the same length as AC, but the length associated with 4-position is something you still agree upon, but you will start to perceive the rate of flow of time differently compared to the stationary observer, because the components of 4-position, so both the time interval and the space interval, will be different. And we talked a bit about time dilation in that video. We're going to now have a recap of that and a recap of this of the invariant quantity associated with 4-position, that is the space-time interval. And then we're going to move on to talking about how the components of a 4-vector are different between different reference frames. And that will lead us to a discussion of Lorenz transformations. If you've seen relativity before, you will have seen Lorenz transformations. You will probably have seen Lorenz transformations with lots of confusing betas and gammas floating around. This video will make, hopefully, the Lorenz transformation far more accessible, because we'll be thinking of it geometrically and thinking of it as a rotation matrix, so something that causes kind of rotation in space-time. And when looked at it through that lens, it's clear that Lorenz transformation as a rotation will correspond to keeping the invariant quantity the same, so not changing the length of the vector, but will correspond to the components of the vector being different. I mean, that's what we mean by rotation. It's just the Lorenz transformation looks a very strange kind of matrix to consider as a rotation matrix, because this is a rotation, but to keep the length preserved as we define length in special relativity, as we define the length of 4 vectors, I should say, in special relativity. And that definition is not compatible with Pythagoras' theorem, so the space we're rotating in is not a Euclidean space. It is space that doesn't obey Pythagoras' theorem, which gives rotation some strange features, which we mentioned briefly in the previous video, but we'll explore more deeply here. So this is a kind of, hopefully, relatively geometrical approach to Lorenz transformations. So to review what we said in the last video, which is relevant to this one, both as a refresher to those who have seen the previous video on the playlist, but also to make this video accessible to those who, want to start the playlist here, because I want to make, each video stand on its own as much as possible, so, anyone can kind of enter at a point they feel comfortable. So in the last video we kind of explored, as well as the idea of the space-time interval, why notions like the time interval, so the how long events take place, is something very unique in terms of how it works in special relativity, particularly if we consider time dilation. And so, when discussing this and the idea that whilst the space-time interval is something, a moving and stationary observer would agree upon, the time interval between events is not. We talked about this hypothetical example where we have an alien who is firing his laser gun vertically upwards, and the laser is kind of being fired towards the kind of ceiling of the carriage on the train this alien is on. So this alien is on this carriage, and this carriage along with the whole train is moving with some horizontal velocity. But the alien, because the alien is kind of stationary relative to the carriage, he doesn't really notice that there is any horizontal velocity, and he's just firing a laser beam upwards, so he thinks the light is just moving vertically upwards. And the distance the light has to move, so if you like the vertical height of the carriage, would be just the speed of light in his reference frame c, multiplied by how long it takes the light to move that distance, so dt prime. However, from the human's perspective, who is standing on a platform watching the train go by, the train, along with the light beam, has some kind of horizontal velocity, because the stationary observer on the platform is watching this train go by, so this train is moving relative to him. And so the light, according to the human, will actually be following a diagonal path, so it will have kind of the horizontal velocity equal to the velocity of the train, but it will also have kind of a vertical velocity because the alien is trying to fire the light beam outwards. And I called dx the distance the train or the light beam has travelled horizontally as the light is kind of travelling, towards the ceiling of the train. And the human will say that the distance the light has travelled, the kind of diagonal distance according to the human, is the speed of light in his reference frame c times the time it takes the light to travel that distance, dt. Now I use c to be the same in both because in special relativity all observers agree on the speed of light, so c is going to be common in both reference frames. Which it most certainly wouldn't be if it wasn't for relativity. But that's a strangeness of the speed of light. So both observers agree on the speed of light, so they both think it has the same value, which we've called c. Well, because the height of the train is the same for the alien and the human's perspective, we can now just link our horizontal distance dx, our vertical distance c dt prime, and our diagonal distance c dt into kind of distances of lengths of a side of a right angle triangle. And putting all these kind of sides of the right angle triangle together and rearranging, we end up with this expression. Now, if you're not confident, take a moment to relate all the sides by the Pythagoras' theorem and rearrange appropriately. But what this equation ends up saying is essentially, providing the alien does have some horizontal velocity, or the train as a whole, including everything in it, including the alien, that is, providing dx is not 0, then dt prime is going to have to be less than dt. So the time it takes for the light beam to hit the ceiling of the train is going to be smaller for the alien than it is for the human. So the alien is going to think less time has passed than the human thinks has passed. And we're talking now about, time interval between the events of, the light beam being fired and hitting the ceiling of the train, but we could talk about it for any events, So we say that kind of time has slowed down for the alien. The alien notices less time go by than the human, and that's a very real fact. You know, the faster this alien moves kind of horizontally with the train, the bigger the value of dx and the more extreme this time interval. And we can also see an interesting thing, that is, if the alien's velocity was going to get very close to the speed of light, then dx would get very close to c dt, because dx is how far horizontally the human thinks the alien, along with the train and the light beam, has travelled. But if the train with the alien on it is moving close to the speed of light, then this distance dx would be almost, the speed of light times the time interval. So dx would kind of get close to c dt, meaning that dt prime will get close to 0. So, in the limit where this alien kind of is approaching the speed of light, or the train as a whole is approaching the speed of light, almost no time will pass for the alien compared to the human, And this effect can get, as strong as one likes. The alien can never reach the actual speed of light because the alien has less mass along with the train, but they can, in principle, get very close, get, as close as they like. And so this time dilation can become very extreme indeed. Now, because time is moving more slowly for the alien, suddenly measuring kind of the time interval between events isn't a very good way of measuring kind of intervals if you're interested in writing equations which all observers would agree upon, because clearly the human and alien do not agree upon the time interval between events. However, they do agree on, the space-time interval. And if we write the space-time interval more abstractly, we can write it in this form, where ds squared is our space-time interval, which, for the alien, because the alien considers itself as having no horizontal velocity, because from the alien's perspective, nothing is moving, including the light beam, horizontally relative to it. So for the alien, it considers itself as having no horizontal velocity, neither the light beam, so dx prime would be 0. So, we can write the alien space-time interval as just c squared dt prime squared, and we don't have to worry about a dx prime at all. But generally, when we say the space-time interval is the same for the human and the alien, in a very general sense, we'd have to go c squared dt prime squared minus dx prime squared is equal to c squared dt squared minus dx squared. So that's where we got to last time, and this kind of like x mu is the components of our 4 vector, I should say contravariant components of our 4 vector, which marks, the 4 position. So x mu has components c dt and x, and also the eta mu nu, the Greek collector with 2 indices, is a matrix, and this matrix kind of introduces this minus sign between the time part of the space-time interval and the spatial part of the space-time interval, and essentially assures that, the space-time interval is a way of calculating distances that ensures the speed of light is preserved, but due to this minus sign, which is kind of contained within this kind of metric, this rule for calculating distances is not Euclidean. It doesn't obey Pythagoras' theorem, because in Pythagoras' theorem the distance that corresponds to the length of a vector would be just the sum of its components. Well, the square root of the sum of the square of its components. Whereas here we're going where the distance squared of this vector includes subtracting some of the components from other components, which is very unlike Pythagoras' theorem. So that was very, very brief, but that was just a kind of coverage of what we did on the previous video. So if you're unfamiliar with that, the previous video in the playlist will go through in more detail, but this is kind of the starting point of this video. The idea that the space-time interval is the same in both reference frames, indicating that the length of a vector linking two events is something both observers agree upon, providing they're using the space-time interval to be the measure of the length of that vector. However, as we can see, for example, the time component, and it also turns out the spatial component of this 4 vector can be different in different reference frames. Here we just looked at the time component, that is the time interval between events, but in other thoughts experiments more generally, you would also have a difference in the spatial components as well. Although you can kind of see it here, because as we've said, for the alien dx prime is 0, but for the human, the alien has a non-zero horizontal motion, so dx wouldn't be 0. So we can see that spatial descriptions and measurements are different. But the real shocker is really the time interval can be different as well. So the alien and human agree on the length of for position as given by the space-time interval. They do not agree on the components for position, and that gives us a hint about the kind of operation that is needed to go from one reference frame to another. It will have to be a transformation of the components of a vector such that the components can change but the length of the vector doesn't. And that kind of transformation is exactly what a rotation is. It's what a rotation is defined to be. So we talked a little bit about the space-time interval, but we can do a similar thing to discuss invariant quantities associated with other 4 vectors more generally. So the scalar product is a way of calculating the length of a vector, and it generally involves a metric. Well, I should say a metric tensor. Technically, a metric is a rule for calculating the length of a vector when you have the components of the vector, but the metric tensor is a matrix which goes into the formula for the scalar product to give this rule. So but because you get the metric from the metric tensor, the only thing that varies between one space and another when you're calculating the length of a vector is kind of all contained in the metric tensor. So sometimes the metric and the metric tensor are just interchanged, because all the information in the metric is present in the metric tensor. So if we want to find the length of a 4 vector, which is something that 2 observers, even if they're moving at relative speeds to each other, will agree upon, we use this matrix. This matrix, which is our metric tensor. And in special relativity, we take the metric tensor to be eta, the Greek symbol eta. It's a matrix, so it has 2 components. We can also think of it as, it acts on a contravariant vector to turn it into a covariant vector. That's another way to think about it. But in terms of the scalar product, our metric tensor is multiplied with regards to our contravariant components of the vector. and that gives us the length of our vector squared. And this is a scalar quantity in space-time, by which I mean it's a quantity all observers agree upon. Sometimes, to make it clear that this is a conserved quantity in space-time, well, I say conserved, really, it's a invariant quantity in space-time. It's a quantity observers agree on no matter their velocity. We sometimes call this kind of square of the length of a vector, we sometimes call it a Lorenz invariant, if you want to be technical. So the space-time interval is a Lorenz invariant, and it's the Lorenz invariant associated with fall position. But fall position is not the only vector we can define in space-time. For example, we could talk about the rate at which the fall position is changing. That is, if you're saying, for example, you've got two events in space-time, because time naturally passes, if we're going to plot these events on space-time, well, because time passes, for example, events might kind of start to drift apart. It's a little abstract, but essentially, if we, like, for example, if we consider a moving car moving in one direction and a tractor moving in the other direction, we might look at how both objects move across space-time, and we can then have a vector or form position linking these two events. That is the, if you like, motion in the present at whatever time the current time is of the truck and the car, and we can see how this form position will change as time is allowed to evolve, so as the time associated with the present kind of keeps increasing. And when you look at the rate of change of form position, you get a vector for velocity, and for velocity, when defined correctly, will give you a Lorenz invariant quantity. And it might not be much of a surprise to what that Lorenz invariant quantity is, because, just as form position has a Lorenz invariant quantity, which is in a space-time interval, which I guess ds squared is units of meter squared, but ds itself would have units of meter. We might also think that, well, for velocity, since its components again, units of velocity, the invariant quantity associated with it would also have units of velocity. Or, in other words, the length squared will have units of velocity squared. And we might ask, what quantity has units of velocity and is invariant? Well, there's only one invariant velocity. There's only one velocity which doesn't depend upon the observer, and that is the speed of light, so it's not much of a surprise. In fact, it almost has to be true by definition that the Lorenz invariant associated with full velocity is the speed of light. There's no other speed that would satisfy that. As in, there's no other speed that would be Lorenz invariant. So, this has been really to show that, yes, we mainly talked so far about space-time intervals because it relates to time dilation, and also fall position is the most natural, easiest vector to begin with. Other vectors are more abstract, but with each fall vector there is an invariant quantity, but observers will disagree on the components of the fall vector even if they agree on the invariant quantity associated with the length of the vector. I would invite you as a kind of like fun exercise, if you like, to consider what the components of fall velocity might be and see if you can end up with an expression for fall velocity which would result in fall velocity having a invariant length. But that's just a task I leave to you if you want to play around a bit. Now we're going to move on to talk about rotations and bring this video to kind of the central idea, which is kind of describing the Lorenz transformation in terms of rotations in space-time. So we've talked a little bit about rotations. We're going to be now more specific on this slide. Now, it's worth saying before that I used the convention that the stationary observer is in the non-prime reference frame and looks at a 4-vector, and the 4-vector here I'm using the symbol V would have components V mu, with the mu not having prime. And that's just convention, you know. Non-prime reference frame is the stationary observer, but it's worth saying, you know, what is stationary is a relative concept. But if we're considering 2 observers, we can always, you know, describe the situation as one of them being stationary and the other observer moving relative to them. And the moving observer we'll look at the same vector in space-time. I say look, really, the moving observer will measure the physical quantities associated with the 4-vector, but we'll measure those quantities as having different values. And the new values of this 4-vector in the prime reference frame are given by the symbol v mu prime. And so if we're considering kind of jumping between reference frames, then the components of the vector have to look different, but the vector as a whole can't change. Its length has to be preserved, and that's to do with rotation of that's to do with rotation. Now there's 2 possible types of rotation, and I might have been a bit sloppy earlier on. Physicists generally are on occasions. We're not really mathematicians, so we don't mind being sloppy, providing it doesn't mess with our physics. In the past, I might have talked about essentially shifting reference frames being to do with rotating a vector, and that is one way to have the length of a vector preserved but its components be different. But there's another way, and that is where we keep the vector fixed, we just rotate the coordinate system itself, so the space-time axes. And because when we're jumping reference frames in special relativity, we're not actually, we're not actually changing something in the physical world. We're looking at the same events just from a different perspective. So it makes sense to actually talk about the new components of the 4-vector as being different due to rotation of the space-time axes. So in other words, the reference frame, not due to rotating the vector itself. So formally, when we're talking about going from the non-prime to the prime reference frame, we're talking indeed about rotation, but it's rotation of the space-time axes, in other words the reference frame, or the coordinate system, not the vector itself. And this kind of thing where the components of the vector are different because you've rotated your coordinate system, this kind of thing is called a passive transformation, because we're not actually changing the vector. We're just changing the axes in which we measure the components of the vector. However, for practical purposes, it doesn't really matter, at least in special relativity, whether you rotate the vector or whether you rotate the axes which you measure the vector in but keep the vector fixed. If you think about it in a Euclidean sense, if you've got kind of an x and a y-axis, and you put a ruler down and you rotate your axes, or you keep your axes fixed and rotate the ruler, the kind of components of the kind of vector the ruler is kind of forming will change in very similar ways. if you're looking at quantum field theory, it is worth saying it is important to distinguish between active and passive transformations, so where you're rotating a vector or the coordinate system, because in quantum mechanics, sorry, not quantum mechanics, in quantum field theory, you're actually concerned with both. I'm not sure if we'll cover that, quantum field theory to that depth in this channel, but it is worth saying that it's an important distinction there. But for our purposes, it really doesn't matter. So I might be sometimes quite slapdash and talk about rotation of a four vector. I've seen, many people do it, and even in some books it's done. So at least in special relativity, that's completely fine. Now rotation is going to have to take our vector and in the prime reference frame and give us new components of the vector it's going to have to take our vector with the components as measured in the non-prime reference frame and then give us the components of the vector but in the prime reference frame. And as we say, this is going to correspond to rotation of our space-time axis, and the thing that is going to be able to cause rotation would have to be a matrix, where if it's rotating a n-dimensional space-time, the matrix is going to have to be an n by n matrix, and that's to ensure that for example, if we look at a full vector in the prime reference frame or the non-prime reference frame, when we go to the other reference frame, we will still have, we'll still be looking at the components of a full vector. We won't be looking at, say, the components of a, vector which suddenly has 6 components or something. So because we want to turn a full vector, well, we want to essentially transform the components of a full vector into new components of a full vector, but we still want to end up with a full vector. The matrix needs to be an n by n matrix, where n is the dimension of the space-time, or in other words, is the dimension our kind of like vector in space-time is living in. Because we have a matrix, this matrix has 2 indices. Mu, because it has to take into account the coordinates in the non-prime reference frame, but it also has an index mu prime because it's going to give us the components in the prime reference frame. So it has 2 indices. Now, because of the rules of tensor algebra, you put the primed index upstairs and the non-primed index downstairs. So it looks slightly strange. Don't worry if you're not too familiar with tensor algebra why I'm doing this. For all purposes, it's just a formality. I'm doing it such that if you would like to do research and stuff, this video is consistent with literature. It's important in terms of tensor algebra. It's not really important for our purposes, though. For this video, the important thing is there's 2 indices, a mu and a mu primed index. And the symbol for the whole Lorenz transformation itself, so entire Lorenz transformation is just capital lambda, which is like a triangle with the base missing. And as I say, this Lorenz transformation is just kind of a rotation matrix, but in a hyperbolic space. So a rotation matrix which is preserving the length of a vector, but preserving length according to the special relativity notion of length, at least in space-time. So now we talked a little bit about the invariant quantity. We're going to move on to the main part of this video, rotations. So rotations, as we've said, is described by our Lorenz transformation matrix, which has 2 indices. One index is mu, because it's taking components in our mu reference frame, non-prime reference frame of our full vector, and it's also got a index of mu prime because it's trying to get the mu prime kind of component of our full vector. So, the mu, well, kind of like the mu component of our full vector, but in the prime reference frame. So, this is kind of like true by definition. We define the Lorenz transformation matrix, so lambda, to satisfy this equation. But if we want to represent this explicitly in terms of the components of our Lorenz transformation matrix, we can rewrite it like this, where I'm using 0 to refer to the time component, if you like, of our full vector. When a full vector is full position, that will mean, the 0th component will literally be the time interval. When it's other full vectors like full velocity, calling it the time component is a bit unhelpful because it doesn't necessarily refer to the time interval anymore. So to get around that, we call it the time-like component. Essentially, it's the positive, if you like, bit of our kind of like length of a vector when we're working out the length of the overall vector. Fuzzy way, if you like to think of it like that. So 0 refers to the time-like component, I refers to the space-like component, and if we're considering something moving in one dimension of space, then space-time becomes two-dimensional. It's one dimension of time and one dimensional of space. And so we can write our full vector as a vector with two components. We sort of call it a full vector because its distance is still defined in terms of special relativity, which most broadly is about four-dimensional space-time. But confusingly here, often for simplification, we can write our full vector with two components. And as yet, we don't know what A, B, C, or D are. We're now going to try to find the rules to relate these components together and thus get a more explicit description for the Lorenz transformation matrix. Well, if we want to relate them together, we have to recall that whilst this Lorenz transformation is free to change the components of a vector, it is not allowed to change the length of the vector. In other words, this condition must be true. In other words, the length in the non-prime reference frame must be the same as the length in the prime reference frame. And so what you can do is you can take the condition that the scalar product of our vector with itself, which will return the square of its length, is the same in both reference frames, and write it out explicitly in terms of the components using the Minkowski metric, which I've done in the second equation from the bottom. So this has to be true because the length of our vector has to be preserved. But then what you can do to get our bottom equation is you can use the Lorenz transformation expression with our kind of A, B, C, and D terms to relate each primed component of our full vector to the non-prime components of our full vector. And then if you substitute in the non-prime components for our primed components in the second equation at the bottom, then you'll end up with this expression on the bottom, which just has our non-primed components related to each other. And the beauty of doing this is now we have a non-trivial equation, which just is about kind of components in a single reference frame. And if we compare both sides of the equation, you'll be able to do something about how the components of our Lorenz transform, so how A, B, C, and D have to relate. And they have to relate in this way, and I encourage you to verify that by expanding out the brackets, which we're squaring. And you'll see for yourself that these three rules at the bottom have to be true. Now, any components we would pick for A, B, C, or D which satisfy these rules would be valid components for our Lorenz transformation matrix. So we could go as wild as we want. We could have really ridiculous expressions for our components. But to make matters simple, we really want to use identities which are more familiar. And thankfully, hyperbolic functions come along for the ride. Because, for hyperbolic functions, so for sine and cosine, they obey a particular identity which is valid for all inputs. So say, x, which is that cos squared of x minus sine squared of x is equal to 1, and that's valid for all values x. Now, this is true because of how we define sine and cosine. If you're interested, they're defined in terms of exponentials, and we will have a look at what these functions look like at the end. But for now, that's not really worth showing, because having a look at the functions doesn't at all make it clear that this identity holds. The identity holds because of because of the way we define these functions in terms of exponentials. But the important thing is that this function holds, and it's kind of the hyperbolic version of cosine squared of theta plus sine squared of theta is equal to 1 for all angles theta. Now, in space-time, because we're dealing with hyperbolic space, we can therefore think of the input into these hyperbolic functions as some kind of hyperbolic version of the angle. But to distinguish it from a Euclidean angle, we use phi for the kind of hyperbolic angle. So we say that the Lorenz transformation can be written as cos of phi for A minus sine of phi for B minus sine of phi for C and cosine of phi for D. And if you use the hyperbolic identity, you'll be able to verify yourself that kind of having the components being equal to these hyperbolic functions will ensure that kind of our three rules are held, and therefore a Lorenz transformation will successfully be able to change the components of a vector, but will not change the vector itself. Well, not change the length of the vector when jumping from one reference frame to another. And because of this, we kind of think of phi as still a kind of causing rotation. It's just rotation in hyperbolic space, so we can think of it as a hyperbolic angle. And phi is kind of formally called the rapidity factor, if you would like to know its name. Now, here we've derived the Lorenz transformation in terms of hyperbolic functions of the hyperbolic angle, but you might wonder, well, what geometrically do rotations look like in space-time? And so we're going in the next couple of slides go through that, firstly talking about circles, because we can get a circle by having a vector and just rotating it along all possible angles. And that will kind of, if we look at the tip of the vector, then construct a space's version of a circle. So circles are intimately related to the notion of rotation. And similar is true for a hyperbolic space. It's just a circle looks very different, as we will see. And then in the slide after the next one, we'll show explicitly kind of, the rotation of a vector in hyperbolic space. So changing a vector such that its tip traces out the hyperbolic version of a circle. So we said we were going to have a little look at kind of rotations, that is the rapidity factor in hyperbolic space, and rotations are inevitably associated with the spaces we're considering version of circles, because we get a circle by having a vector and just rotating it along all possible angles. So for Euclidean space, 360 degrees. If you have a vector and do that, you rotate it by 360 degrees, but keep its starting point fixed, then the vector will trace out a circle where, each point on the circle will lie at a constant distance from the centre, because, there's this vector that links the centre of the circle to this point on the circumference. Sorry, that's my dog, Molly, barking. But this vector is by definition going to have fixed length, because that's how we construct a circle. Molly's very excited, I do apologise. But essentially, we get a circle by just rotating a vector. And we could do a similar thing in our hyperbolic space of spacetime. We can consider for position, and we can consider rotating for position across all possible angles, and that will result in a curve which we can call a circle, but for hyperbolic space, where all points on the circle, well, I should say the circumference of the circle, will have, a constant distance from the origin. So in other words, a constant space-time interval. And this is what we have for hyperbolic space. Now this looks very unintuitive because we're not used to thinking of rotations in hyperbolic space. Our mind is hardwired for Euclidean space. In fact, these circles, if you like, to us look like hyperbola. Because a hyperbola is a shape, at least if we're considering, a one-dimensional hyperbola, it's going to have as a function the equation x squared minus y squared equals a constant. But that's by definition, if x is the spatial component of our full vector and y is the time component of our full vector, then by definition the equation of a hyperbola will define essentially points for which there is a invariant kind of like distance, which for full position would kind of correspond to the space-time interval. And we've got kind of multiple circles here, so the two green lines actually form a single circle. It's a circle which has a radius, if you like, if we're using very Euclidean language, of 0. That is, it's essentially, if there's a space-time interval linking to events in space-time, and that, and kind of like, we're looking at, well, and this kind of like full vector has a distance of 0, so the space-time interval is 0, then kind of like if one event is at the origin of our coordinate system, the other event will lie somewhere along one of these two green lines. That's what we mean. So if the origin of our coordinate system space-time is one event, and there's another event which is at 0 distance as far as we define it in space-time from that event, then our vector will linking those two events will lie along one of these green lines. And we saw in the previous video that the space-time interval is essentially 0 for light. So for anything that is moving at the velocity of light, the space-time interval between, in fact, any two events would be 0. And these two green lines define a light cone, something I'll talk about more in the next slide, where I look at kind of rotation after we've had a bit of chat about these circles. But apart from the green lines, we have two other circles, if you like. We have the red circle, which corresponds to, a radius, if you like to think of it like that, of 2 units, and we have our blue circle, which has a radius of 10 units. An interesting thing is, because these hyperbola form finite circles, that is circles of finite radius, the hyperbola never actually meet. So in other words, if we're considering kind of like space-time intervals between events where that space-time interval is finite, then if we consider all kind of second events from our initial event, which will have a constant space-time interval, we don't end up forming kind of points on a closed curve like we would in Euclidean geometry. We end up forming a disconnected shape with gaps in it, or at least what to us looks disconnected. And that means that for space-time, there is no repeating nature of angles, at least providing the angle is allowed to go to some finite value, unlike in the Euclidean sense. So in the Euclidean sense, if we have a circle, and we rotate a vector, if it starts at what we define to be 0 degrees, and we rotate it 360 degrees, it will end up exactly where it began. So 0 degrees is the same as 360 degrees, is the same as 720 degrees. This is not the case in hyperbolic space if we look at hyperbolic circles, or to what we would call kind of usually hyperbola, because these kind of like circles in hyperbolic space are actually disconnected. So they don't form a closed curve, meaning that actually any finite angle, if it's a hyperbolic angle, will be distinct from any other finite hyperbolic angle. So phi equals 0 and phi equals 360 describe vectors which are at different angles. And it's actually that prevents kind of, for example, sine and cosine having any periodic nature, unlike sine and cosine, their Euclidean counterparts. So that's just a brief note about these kind of circles, if you like. Now we're going to relate it very explicitly to rotations of a full vector. So for this, I've taken my kind of circle, if you like, with a radius of 10 from the previous slide, and I've drawn from the origin of the coordinate system a line, if you like, which is representing a 4 vector, such that the end of the 4 vector touches a point on this kind of hyperbola, so the hyperbolic version of a circle. And so each of these lines represent a vector with the same length, but the vector looks different because the components of the vector are different. The time component, so the component along the y-axis, and the spatial components of the component along the x-axis are different for each of these different 4 vectors. But it's essentially really the same 4 vector, just when we've rotated our space-time axes, so its components look different. So here I've shown the same 4 vector, but I've essentially rotated our space-time axes, which as far as rotation is concerned has a very similar effect to keeping the space-time axes fixed but rotating the vector itself. And we can see that kind of like, if you rotate it, the vector, it traces out this hyperbola, if you look at the tip of this vector. But I've only chosen this portion of the hyperbolic circle, if you like. I've only chosen the upper portion, and that's because if we're considering a 4 vector as observed, or 4 vector whose components are observed by something in the physical universe, that something could either be something that doesn't have any rest mass, so something like light, or it could be something that does have a rest mass and positive rest mass, like me, or like you, or like the laptop, or my cat Arwen, or and therefore, because of that, the maximum speed of an observer that has rest mass is going to be a speed that approaches the speed of light, although an observer with rest mass would never actually get to the speed of light, and the maximum speed that light can travel is the speed of light, and therefore the maximum speed anything can travel in the universe, as far as we have experimentally confirmed, at least if we're ignoring general relativity, is um, kind of the speed of light in a vacuum, and therefore the four vector will have components such that it will always the four vector will always seem to appear in this kind of light cone, if you like. Now you might ask, what happens if something is travelling faster than the speed of light? Because it's often said mistakenly that relativity says something can't travel faster than light. That is not what relativity says. Relativity entirely permits things to travel faster than light. It just says anything with a rest mass can't travel faster than light, and also light can't spontaneously change its speed in a vacuum, because light is a universal constant. So unless universal constants start changing their value, the speed of light isn't going to spontaneously increase or diminish. However, if something is travelling faster than the speed of light, that's entirely allowed by relativity. But if you travel faster than the speed of light, you're in a different light cone. You're going to be seeing events in a different light cone. Because if you travel faster than the speed of light, then your value x, the distance you travelled in space, is going to be greater than ct. So you're going to actually have a light cone which is actually not vertically orientated but horizontally orientated. So, if you're, for example, a tachyon, which is the hypothetical particle, which special relativity allows in principle to exist, whether it does exist or not is a very different matter, but that is going to have a horizontal light cone, at least if you're placing your time axis to be your vertical axis and your space axis to be your horizontal axis. So, light cones in other parts of this diagram, so in other words, other regions of this, if you like, hyperbolic circle, do have physical significance. Equally, you could ask, well, what happens, what does the bottom hyperbola mean? Well, when I've talked about all events in space-time, I'm talking really about events in space-time between something that happens now and something that will happen in the future. If we consider rather, four vectors like four position linking events between the present and the past, then that four vector would lie in a light cone, which is like the light cone we can see here, but just split over, so it will point vertically downwards. And so because of that, essentially all four vectors in the universe, no matter an observer, will have components which will lie in a, vertically orientated light cone. If it's, if the space-time, if events are, well, if, we're comparing space-time events now to space-time events in the future, the four vector is going to have kind of its components such that the four vector lies on the, upward vertical light cone, whereas if we're comparing events now to events in the past, the four vector is going to have kind of components causing the four vector to point along the downward vertical light cone. And as I say, horizontal light cones possibly are significant in the universe or not, but they do describe equations which are entirely permitted by special relativity. So now we've seen visually the rotations in hyperbolic space, where this rotation is caused by a Lorenz transformation. Let's go on to try to kind of like use our intuition that Lorenz transformation is describing both rotations in space-time of a four vector, well, I should say really rotations of space-time axis, whilst the four vector is fixed. But our Lorenz transformation is simultaneously changing the components of a vector in one reference frame to another, where this difference is going to become more and more significant the greater the difference between the velocities of the two observers. So we've now talked about rotations in a hyperbolic space. We've seen visually what this looks like. We're now going to use our kind of geometric and physical intuition to understand more about this rapidity factor, this angle of rotation phi. Now, as we've said, whilst mathematically, if you're considering a mathematical space, there's no reason to relate, a hyperbolic angle to velocity, but because we're doing special relativity, the rotation in hyperbolic space, as a reminder, is meant to represent rotation of space-time axes, where this rotation happens to kind of mathematically describe the changing components of a vector when jumping reference frames between kind of a stationary observer and an observer which is moving relative to that stationary observer. So clearly, using the fact that, this whole bizarreness of hyperbolic rotation is meant to refer to the idea of jumping reference frames, with those reference frames having, differing velocities. Clearly, the hyperbolic angle for our purposes is going to have to be some function of velocity v. And since this change in the components of a vector is kind of ultimately entirely caused by the relative velocity v and nothing else, providing we're considering the speed of light to be just a universal constant, then the rapidity factor is only going to be a function of the velocity v. There is nothing else that is varying which is going to impact the angle we have to rotate our space-time axes. So clearly the rapidity factor is a function of v, the relative velocity between the observers. And we said before that our Lorenz transformation, when expressed in terms of our hyperbolic angle, or our rapidity factor, looks like this. Now, however, I've wrote, instead of phi, I wrote phi as a function of v to explicitly imply that this angle phi is going to have to be a function of v, where v is a velocity in physical space. And we really want to get towards an expression of the Lorenz transformation that is a function of velocity, which is why we're doing this. Because we might mathematically describe in an abstract sense jumping reference frame as rotating angles in space-time by a hyperbolic angle, but because that's so unintuitive and highly technical, we don't really want the Lorenz transformation to be expressed explicitly in terms of the hyperbolic angle. We want the Lorenz transformation to be expressed in terms of the velocity v of the moving observer, and also probably the speed of light. So we really want an expression for phi of v. But we know that whatever phi of v is going to have to fit into these hyperbolic functions such that this is a valid expression for the Lorenz transformation. Now we're going to try to get towards knowledge of what the components could be, and therefore what phi of v might be for some particular special values of v. So the first special value of v is v is 0. Now, to work out what the Lorenz transformation will have to look like when we set v equals 0, we can just use a fairly evident fact that we all find, including myself. It doesn't matter how many years you study physics, one still finds inevitably Lorenz transformations, relativity, hyperbolic space, all of this very unintuitive. And this tells us that based on the velocities things are moving at in daily life, the effects of relativity are are kind of, at least in an obvious way, ignorable, at least the obvious effects, meaning things like we can consider the time interval between events to be, practically the same for, n to observers. If we didn't find that this whole thing, so, if we didn't find relativity so unintuitive, then that would imply that we had naturally built an intuition, meaning relativistic effects would be very evident as v goes to 0. But relativistic effects are not, and that tells us that the effect of relativity should die away as v goes to 0. Therefore, for example, if we take our 4 vector being for position, for example, the components of the 4 position by definition is the space interval and the time interval. Well, we said that, for example, if we look at the time interval, the time interval between events, we would intuitively expect to be the same for different observers as the relative velocity goes to 0. So in other words, the components of this 4 vector we would expect to remain unchanged, or to start to become to better and better approximation unchanged as v goes to 0. In other words, when v is 0, the Lorenz transformation doesn't transform at all. The Lorenz transformation does nothing to the components of the vector. In other words, the prime and non-prime components of the vector are the same. Or in other words, we don't rotate our space-time axes at all when jumping observers, and therefore the Lorenz transformation has to be the identity matrix, because it's only the identity matrix which will be able to multiply a vector and give you a vector with the same components as the original vector. So when v is 0, whatever our rapidity factor is, whatever phi as a function of v is, the Lorenz transformation is going to have to become the identity matrix. And this is essentially a very technical way of saying, well, time dilation is very unintuitive, and we expect time dilation effects to go to nothing as v goes to 0. So that's our first kind of very confident assumption, and very valid and reasonable assumption about the components of the Lorenz transformation. Now the other extreme is where v goes to c. Because it's special relativity, we're considering we can't do v goes to infinity. Well, we can if we're worrying about tachyons, but we're not worrying about them in this video. So, our kind of upper limit, which, light can obviously reach, but which objects with less mass can't quite reach, is the speed of light itself in terms of the velocity of these things. So the biggest physically meaningful velocity we can consider for at least everyday objects is a limiting value of the speed of light. So what happens, or what should we think would happen as v goes to c? Well, before we had an equation for time dilation, if you remember at the start of this video. And we said the time dilation becomes more and more extreme as v approaches c. Now in the limit where v becomes c, time dilation becomes infinitely significant. And what that ends up meaning is that essentially time moves so slowly in the primed reference frame compared to the non-primed reference frame that if any finite value of time has passed in the non-primed reference frame, no time at all has taken place in the primed reference frame. Essentially, time has slowed down so much that, if there's something that takes a finite amount of time for the stationary observer, then that will happen in 0 time according to the moving observer. Or flipped another way around, time dilation has become so extreme that we could flip it around and go any events that take a finite amount of time from the moving observer's perspective, from the stationary observer's perspective, would appear to take an infinite amount of time. So you can flip it either way. But the important thing is that if we have a finite value for, say, the time components of forward position, then in the limit v goes to c, the time component in the prime reference frame should be 0. The time interval should be 0. And if we, consider, well, what is also the forward position in the non-prime reference frame when v goes to c, well, in that case, bearing in mind dx is how fast the moving observer, how far the moving observer has travelled. Well, if the moving observer is moving at speed c, then they've travelled a distance ct, or I should say c dt if we're talking about time intervals formally, in which case both the time and space component of forward position in the non-prime reference frame would be just ct, so importantly they would be the same, the components would be the same. And when we look at our Lorenz transformation, given that the components in the non-prime reference frame are the same, but we need the first component of our forward position in the prime reference frame to be 0, we can say that the limit as v goes to c of cosh of the rapidity factor minus sine of the rapidity factor must equal 0. And here I've expressed it more formally, So, it's worth saying I've used a bit of tensor notation where I've, wrote lambda naught mean prime. But, that's just kind of technical details for those of you who like tensor notation. But the important thing is we also have this limit that will be kind of expected. So based on what we've said so far, whatever the rapidity factor is, whatever phi of v is, we have the case that cosh of phi of 0 would be 1, but sine of phi of 0 would be 0, and also the limit as v goes to c of cosh of phi of v minus sine of phi of v would have to equal 0. So I suppose in a sense really we've got 3 limiting conditions. Now it's worth saying that here we talked about the limiting conditions in terms of hyperbolic functions of the rapidity factor. We would really like limiting conditions in terms of the rapidity factor itself, and that's what we'll talk about in the next slide, where we'll kind of conclude this video. Hello, so on the previous slide we looked at limiting cases for hyperbolic functions of our rapidity factor to get a firm idea, however, for kind of how hyperbolic space, well, hyperbolic functions at least, would imply, based on those limiting kind of values for the rapidity factor itself, we need to look at what sine and cosine of hyperbolic functions actually look like. Well, here is sine and cosine. So sine is our red curve, cosine is our green curve. It might be tempting to look at them to go, well, they look like sine is a cubic polynomial and cosine is a quadratic polynomial. That's not the case, however. These curves are, as I said before, defined in terms of exponentials. Now, based on these curves, we can relook at our kind of 2 limiting cases. Well, we said before that cosh of phi of 0 would have to be 1 we can kind of compare the components of these kind of 2x2 matrices. But if we look at our graph, cosh of something is only 1 when that something is 0. So in other words, if cosh of phi of 0 is 1, then phi of 0 would have to equal 0. And you can say similarly something about phi of 0 if you look at the sine curve. Now, also, if we look at the limit as v goes to c, and that kind of limit on, hyperbolic functions of our rapidity factor, then looking at our hyperbolic functions, we can see, well, essentially, if we rephrase this limit as saying as v goes to c, the hyperbolic functions have to meet, then that tells us that kind of, as v goes to c, the input to our hyperbolic functions has to be infinite, because it's only at infinity that our curves actually meet. Because the curves get very close together very quickly, it might look like they meet from this graph a lot closer than kind of infinity, but they actually only get asymptotically close. Only as x goes to infinity do our curves actually approach actually meeting. Essentially, we have these two limits on our rapidity factor. Now, we might kind of intuitively kind of expect this because we said before that our rapidity factor is really a hyperbolic angle. So if we consider firstly our solution that phi of 0 has to be 0, well, remembering phi is a rapidity factor, it's kind of the angle we rotate spacetime axes by to jump between observers. But if v is 0, then we would kind of intuitively expect, well, there's no kind of angle between the spacetime axes for the primed and non-primed reference frames, because because v is 0, so there shouldn't be any rotation at all. And so we would kind of intuitively expect that phi of 0 would have to be 0 based on our geometric understanding. Phi of v as v goes to c is a bit more complicated. Phi of v as v goes to c is kind of like the maximum angle. But we saw before that circles, if you like, in hyperbolic space are not kind of closed curves. And so we can define essentially a kind of like any two distinct values of phi correspond to a different amount of rotation of our space-time axes. And therefore it doesn't really make much sense to set the maximum rotation to a finite value, because you could ask, well, if we set the maximum physical angle, if you like, of rotation to a finite value, then what would it mean to rotate a vector to an angle beyond that? Because, as we said, there's no finite upper limit in kind of how much you can rotate a vector in hyperbolic space. And each finite value of phi is distinct. So to get around that, we would really need to say, well, the all possible values of velocity have a unique value associated with them of phi, and since all values of phi correspond to unique angles, providing phi is finite, then essentially our maximum possible velocity would have to correspond to an infinite value of phi. And that just gets around the problem of defining a maximum finite value of phi to refer to v as c, and then having to ask, well, what happens if we rotate a vector beyond that finite value? So setting, phi of v as v goes to c to equal infinity just completely gets around this problem. We've essentially rotated our angle, rotated our space-time axes to the maximum possible angle. So that's kind of a slightly more wavy, but hopefully fairly sensible justification for that limit. Now you might see that I haven't yet actually defined phi as a function of v explicitly. I've just got to a point where I'm giving limits for what this function could be at particular values for the input v. Now I'm going to leave this video here. In the next video we will, based on what we have done here, derive an explicit representation of the Lorenz transformation in terms of v, which essentially reduces down to working out what the rapidity factor is as a function of velocity. But I would encourage you to see if you can guess what the components of the Lorenz transformation matrix will be in terms of velocity v and the speed of light, based on what we've done on this video, because we've covered enough for you to do it, and it's a good little challenge. And for that I would recommend using the idea of time dilation to derive explicitly one of the components of the Lorenz transformation as a kind of function of velocity v, and then use the fact of how these components have to relate. So in terms of hyperbolic functions of our rapidity factor, to therefore work out the other components. And for this you might have to use the identity for your hyperbolic functions. So that's what I would kind of recommend doing if you would like a bit of a challenge. And it's also a good reason to leave this video here, because it leaves you to have the fun of kind of deriving something for yourself based on what we've done, and a good way to check have you derived the correct Lorenz transformations is does the corresponding rapidity factor obey these kind of limiting values. So does phi of 0 equal 0, and does phi of v go to infinity as v goes to c? Now this will be the last video on this playlist for probably a couple of weeks. At the moment I'm working on a novel, doing a few things, and so because of that I will probably be leaving kind of updates to YouTube generally for a couple of weeks. However, there's kind of lots of content on this channel, so we'll hopefully, if you're interested in kind of exploring all this, give you also time to kind of explore some of the content without kind of new content being uploaded for a bit. Kind of like what I have to do with catching up with audiobooks. Got lots of audiobooks I haven't much got through, so over the next 2 weeks I'll probably be catching up with those. But this feels like a fairly good point to leave it. It's worth saying that I will also be continuing the quantum field theory playlist as well after the next couple of weeks. And also the next couple of weeks I'll be reading some physics to go over some stuff and learn more physics, because I myself am always trying to learn more. And therefore hopefully come back to this channel with kind of new and refreshing insights as well. But as always, if there's anything you would like me to improve upon in this video, please let me know. And also if there's any topics you would like to cover, also let me know. And hopefully see you for more videos soon.